Hello, Water Managers. I am Alex Davis. I am with the Water Management Systems Division out at the Hydraulic Engineering Center. In this video, I'm going to cover real-time hydraulic modeling forecasting tools. So the main objective of this lesson is to learn about what forecasting options are available in the category for hydraulic modeling, i.e. HEC-HMS. Then we'll discuss how to effectively calibrate an HMS model. So this is the second video in a series. The first video we talked about model calibration. If you haven't already watched it, I recommend going back and watching it. This video, we're going to talk about forecast-specific editors. So we're going to talk about zone configurations and zones, zonal editors and elemental overrides, and how they can benefit us. And then we're going to look at the initial base flow reservoir and blending options available for the forecast-specific editors. And then there'll be another video in this series on the HMS CAVI integration. So let's get going with forecast-specific editors. HMS has some forecast-specific editors that will only show up when you're working with the forecast alternatives. These can be seen under the Compute tab after the Compute type managers are seen as seen here. So we have Compute tab, we have our managers, and then down here are all forecast-specific options that we have available. You can make changes in the editors reserved for forecasting and will apply only to the forecast. With this said, it is possible that you might not see changes in a forecast editor if you change the basin model. So there's something to keep in mind. You'll notice in the example below, we actually have a variety of basin and MET models. So over here, we have a summer large rain, a summer routine rain, we have a winter rain, we have a winter rain on snow for the basin models, and then for the MET models, we have rain, and then we have a rain and snow MET model. So why do we have so many? For real-time modeling, we need to be quick. And one way we can be a little bit quicker is we have all of these options already in a calibration range for these situations. And so, of course, the summer and a winter event aren't going to be the same. But then even like in the winter, we have the winter where it's just a rain event. And then we have a winter where it's rain on snow. So these are going to be set up a little bit differently. And so it should be a better starting point for an event that we're anticipating. And then likewise with the MET models, depending on what we're looking at, we might just be looking at a rain event. We might be looking at something with rain and snow. And so when you incorporate snow, a lot of times you'll have to incorporate temperature as well. And so these are just some ways that we can make our forecasting a little bit quicker. And so we can get a product out earlier on. And so another way of doing this is we use zone configurations and forecasting. The zones allow us to group subbasin based on various model constraints. Maybe we believe a handful of subbasins should be grouped together based on characteristics. So let's look at the 5-zone example on the right. Maybe these have characteristics that mesh well together, and so we believe that we should have it zoned this way. Or maybe like on the left, we have 2 observed gauge points, and so we're going to group everything upstream of one observed data point and then another one. And so we can do some calibration based on available data. So this is a more common approach that we see. So we'll have zones based on observed data. And we'll see in a couple of slides on how this can actually be beneficial and make it a little bit quicker for our calibration process. And so if we don't know how to do the zone configuration, it's actually pretty simple. We'll open up HMS and we'll go to the parameters, and then we get this zone configuration manager. Then we get the zone configuration manager over here. We just hit the new button and we type in a name. So these names need to be something that makes sense to you and your team. Sometimes it's going to be something really straightforward, like how we have here. We have how many zones we're breaking our subbasins into. Other people might prefer a different process, and so just make sure that you create your names in accordance to what makes sense to you and your team, or what is already being done. And then once we have our zones created, we can add our zones to it. And so in our 3-zone example, we have the central, north, and south zones. And then once we have all that situated, we can click on the elements, and then you'll notice up here in the top right of this dialog, we have zones north, and so we're adding elements to this north zone. And so this can also be done with items outside of the subbasin. The reaches, you can zone reaches, but most of the time for forecasting, for real-time forecasting, we're just going to do zones based on subbasins. And so the zones really come in handy with our editors. And so this is an example of our combined parameter editor, which is where we'll do most of our calibration. But what we want to bring up here is on the top frame up here, we have our zones. And so this example, we have these 5 zones all named variously based on 2 of them are based on reservoirs and the other 3 are based on location in the watershed. But then we group all these together to make these modifications. So currently we have the middle selected, and we can see down here, these are all the subbasins within this middle zone. And we can modify this entire zone by several methods, including using an asterisk and then a number. This is just multiplication. So in this case, we're multiplying just about the entire zone by this value of 2. So if we look down here in the initial deficit, we can see all these subbasins we can see have a value of 1. We have the asterisk 2. And so it's forcing almost all of these to have an initial deficit of 2. Likewise, we can do addition and subtraction, seen here, or we could even just put in a number. So over here for this middle one, the zone average is 0.077, and we want it to be 0.06. And so you can see through here, it doesn't matter what this base value was, all these final values are at 0.06. But then, let's say we have a subbasin that we don't feel like is responding the same as all the rest. We can do an override with that as well. So there's a checkboxes over here. So we have an override going on here, and we can type in the value that we want. So instead of 2 for this initial deficit, we felt like 1.5 was more applicable for the situation. And so we went ahead and did this. This is why zones for forecasting can be so powerful, and that we can group lots of subbasins together all at once to do our calibration. And this is also why we commonly will have zones based on observed data points. And then just want to point out that in the bottom left, we have this compute that's going to use the computational control points as well. And so that we can have a drop down, go through our compute points, and run just a section of the model. And so a lot of times each one of these zones is going to have its own computational point. And so we can, as we go through the calibration process, we can choose what we want to do. So now that we can see how the zones and element overrides work, let's look at the more explicit calibration parameters that we're going to be looking at. So here is initial base flow. This is one of the custom interfaces that we have. Here we can use an observed discharge gauge value and force it to base flow of a subbasin. So in this example, we're looking at the base flow zone up here, and we have 3 subbasins in here, and we're selecting a discharge gauge for all of these. And so we're dictating what the discharge is. And so the observed discharge for here is this 312.2 CFS. But then we apply a ratio, and this ratio for this one is done by the percentage of the drainage area for this zone. And so we can see that bald eagle is about 1/4 of the entire area of this zone. And therefore we're associating it with 1/4 of this base flow, which pushes it down to about 75 CFS. On this note, the initial baseflow editor overwrites the basin model and zonal editors. So if you're making changes to the model's baseflow and you're not seeing a change, it's most likely it has to do something with the values populated in its interface. And there's other interfaces that will behave similarly to where it's just going to override the various values that you have. And then we have our reservoirs. We can change how HMS handles reservoir discharge when it runs out of time series data and the starting pool elevation. In the bottom window Here, we can set the observed gauge location for both the start of the model and the start of the forecast time. This will match the stage at the first time step to make sure that we are starting on the right foot for our calibration. Then we have the discharge time series data handling after forecast time for all reservoir options. Um, since once we go through the forecast time, we don't have observed data anymore. So we're telling HMS how to handle this situation. So we get three options for how HMS is going to do this. We can tell it that we're just going to replace the missing with the last value. This will generate a straight line from the last value and maintain this discharge. We can tell HMS to replace the missing with 0. And so this is just going to make the discharge 0, 0 flow. And the last option is going to replace all with 0, even if there is observed or specified value after the forecast time. And so the last feature that we're going to talk about that's forecast specific is blending. Blending is a forecast alternative option that we talked about very briefly in the last video. This allows for us to override values from our calibration values to be observed values. This helps make it to where the error from imperfect calibration does not impact the downstream in the calibration process. Since we are working in the forecast alternative, we do not have observed data for the entire time window. This is when we incorporate blending methods as shown in the right image. We have the options of none, step, and taper. None applies no correction to the computed stream flow after the forecast time. The step method applies a fixed correction to the computed stream flow from the forecast time to the end time. Then we have the taper option. This option applies a decreasing correction to the computed stream flow after the forecast time. So over the taper time selected, we will gradually decrease the correction, and by the time the taper time allotment has been achieved, the correction is complete, and we only have the computed flow from HMS. So those were the main topics of this presentation. If you have any questions about our software, need some help, or are looking for additional training, check out the links that can also be found in the description below. Thank you so much for your time and hope you have a fantastic day.